Right, thanks. So today we'll be presenting our work titled Fully Convolutional Neural Networks for Dense Water Flow Intensity Prediction in Swedish Catchment Areas. This is in collaboration also with Olof Mogren, also at RISE with me, as well as Morten Westerdahl, who is at Kungsbacka Municipality. And me and Olof, we are working quite broadly within the AI for environment topics, and our research group is always interested in discussing different types of collaborations and similar. But moving on to the topic of today then. So the motivation behind our work is that with intensifying climate change, there is an increasing need for better flood risk mapping. And this applies to Sweden. For example, we had a couple of years ago the quite massive flooding in Gävle. But also, of course, on a global scale, there are many regions of the world that are very severely affected by extreme rainfall events and similar. So with this motivation, we started a collaboration, as I mentioned, with Morten Westerdahl, who nowadays works with the climate adaptation aspects for Kungsbacka Municipality. But when we started out, he was also working at RISE. And we started to do a pre-study for some ideas that we later expanded within this present work, where in the first step we did modeling for water flow intensities in catchment areas, in particular the Kryckland catchment area. And the catchment area can be seen as a geographical site where you may have a bunch of sort of rivers and streams and similar, but where all of these streams have sort of a common sink, or sort of a, you can imagine it as like as a bottom of some valley or similar, where the water accumulates in the end. So there are a bunch of these types of areas, including areas where there are actually measurement stations that provide us several decades of time series data for daily averages of these water flow intensities. And this is what we wanted to use in our work, being able to predict these types of properties. And as I said, we expanded this to several geographical sites in Sweden. And going back to the background and motivation, then some future possible use cases of the research that I will explain, and more broadly, of course, what others have been doing in this area, is, for example, related to increasing the possibility to predict flooding and erosion, but also to assess nature-based solutions such as wetlands. How can they be restored and similar to have better effects of actually avoiding, in some sense, flooding by capturing it in the ground. So now we will start moving on to what we have actually done in this work, and I will explain it sort of with the Kryckland catchment areas as a starting point, as just an example. So here you have a map of the area where you have small yellow dots. Those are the measurement stations where they're actually measuring daily averages of this water flow intensity, sort of the volume per unit of time that is passing there. And the question that we had is, okay, so assuming that we have rainfall occurring in the region, and then you have, it's been raining for a couple of days, for example, how does that affect the predicted or the actual water flow that is running in this area? And you can note that the flow map that we provide is actually a map that has the same size as the input map, so to say, indicated as the red rectangle in this case. And therefore we tackle a task that is novel, really, which is water flow intensity prediction in a dense way. So dense water flow intensity prediction, which means that we want to be able to take some time series of temporal information. I'll get back to what that is, for the past several days. And using that as input, we want to predict the water flow intensity in every coordinate of the input map. And to sort of contrast this with prior works, they have mainly considered doing it, but for the actual measurement sites that you have, not the whole area overall, which makes them, I would say, less general. And we want in the longer run to be able to use these also in places where you don't necessarily have the measurement stations themselves. So now we'll start talking about how we have approached this dense water flow intensity task. So we had the rainfall in the region, and we also took another commonly available time series, which is that of temperature. So we have daily average rainfall and daily average temperatures, and we feed them to a model, which I will get back to what the model is. And as I said, the rain and temperature are actually time series like that. But in order to get actually a flow map that gives us like the spatial variability, we also provide a model with spatial inputs. So the model is like spatio-temporal in a sense. It integrates both space and time in the following manner. And given that we want to work with dense predictions, we opted for using a fully convolutional approach in this work. And I will now go on to explaining exactly how this is being done. So we have a bunch of these geographical sites that we have in our data with these publicly available time series and so on. And for the spatial inputs, we have opted for using 8 different ones. The nice thing about Sweden, and I would assume many other parts of the world, is we have a bunch of spatial data that can be used, in addition to the commonly available satellite imagery, for example. We also use elevation maps, terrain slopes, land cover, different types of soil property maps, and hydraulic connectivities. And these are provided by different agencies and are also like freely available for use. And we do something quite obvious. We just concatenate these types of maps into a volume like that. As for the temporal inputs, well, as I mentioned, we work with rainfall measurements as well as temperatures. For the past T days, we used 20 days mostly in the experiments, but the model wasn't very sensitive to that. And for this part, we also want to sort of create it into sort of a volume, which this is for it to match the fully convolutional model that we have. So we do something which is fairly straightforward, but it actually worked quite well, which is you just take your vector of 2t scalar values, and then for each of the scalar values, you create just a channel of dimension h times w, where every value in that h times w channel has that scalar value in it. So it's like a constant map, which gives you this hw to t-dimensional entity. And just to be clear, we could have used also the water flow intensities from the past days as input if we want. And we did some experiments with that as well. But as I said, we want the model to be more general. We don't want it to rely on that type of information, which is not very often available. So we did not typically use past water flow intensity information in the model. So revisiting the bigger picture, this is a summary of what we did then. We take the spatial inputs into a volume, we take the temporal inputs into a volume, concatenate the volumes, feed it to the FCM, which gives us the predictive flow map at every coordinate, which was precisely the sort of the task at hand, just to remind you. So how to train this system then? Because yeah, with predicting dense predictions, but we only have measurements at a very sparse set of points, typically only 1 point, but for Krypton we had in sometimes several points. So we use the loss only in those sites, and you can imagine it as, you have a loss function, and you only provide it in certain pixels. You ignore the predictions in the other points, and then you train the model. As the loss function, we use the Huber loss, which is like consists of 2 statements. The first row is giving you like an L2 loss, the typical mean squared error loss. And the other alternative, if the error gets too high, then it switches to the L1 loss, which makes this model less sensitive to outliers. So how do we create these training examples for the training process, etc.? Well, let's zoom in on one of these measurement sites in yellow. So I make it into a larger yellow dot for zooming in. What we noted here is that, we have a rectangle of size h times w, but that rectangle can be positioned in many different ways relative to the measurement site, which in effect gives us a bunch of training data for creating training batches. So the only requirement is that the rectangle contains at least 1 measurement site. So we trained it in a fairly straightforward manner. Won't go into the details here, but moving on to the results here. The first result is we can see training and validation curves during a training process, where the blue one is our main model, the machine learning FCN model. And then we compare it to 2 baselines. The red baseline is what you get. If you take the water flow intensity time series, and you take for each different site that you have, you just compute the mean of the whole time series at that point. So that is in some sense the optimum solution that you can get if your model is not relying on the rainfall or temperature information, because then it could sort of get the best average guess, which is time independent. And that's just to see like what a very naive solution would give. On the other end of the spectrum, we look at a model which copies, it's a sheeting baseline, but then kind of to see how small the error would get, but it copies the previous day's water flow intensity value as the current day's intensity value, and that's a very good guess typically, which gives you something which is sort of better than our model. But to repeat, our model is never given those types of information. It's never given water flow intensity information, only rain and temperature. So it doesn't get that good. We hope to continue in this line of work to narrow the gap, obviously, in future. Looking at a bit more numerically, these are the same set of values that we see on the right. But then we did some ablations also, where we removed some spatial inputs from the model. So we have three examples shown here. If you remove the elevation information, or if you only use the elevation information and so on. So, I mean, as can be expected, the elevation information is very important, but it's not sufficient on its own, because if you only use elevation information, you get a much higher error than if you have all the inputs, for example. Also, we try to remove certain parts of the temporal inputs. So if you remove the temperature, you get a slightly worse results. If you remove the rainfall, you get a really, really bad results, as expected. As for this thing I was mentioning about using the past flow information, our main models do not leverage that, but we wanted to see how good can it get if you actually feed previous flows into the model, and it gets significantly better. Essentially, this t minus x is just until what point in time do we provide the flow information. So t minus 1 is the day before, for example, and it gets much better. But it's also not available in most cases. So yeah, as I said, it would be nice to keep shrinking the gap between such models. A couple of qualitative results just to conclude. So in the top left, you have the predictive flow map for this particular example, where you have 7 types of inputs maps shown here. If we, for example, then look at one of the particular types of input, the terrain slope, which is one of the main important maps, you can see a very similar pattern. You have kind of like a Y shape, for example, that is blue, which means that is little predicted intensity. Whereas in the higher slopes, you also have higher water flow intensity prediction, which makes sense. Another example, which has a little bit less structure, I would say, in terms of the slopes and so on. But also in this case, it can be seen roughly a similar pattern, that the higher predicted flows are sort of corresponding to where the slope is higher and vice versa. Yeah, so that's it. We introduced in this work the task of dense water flow intensity prediction, and we were able to show early results now where we can get such models by training only on a very sparse set of points. Our models do not rely on past flow intensities as input. It's been interesting to see that we have some collaborators at Sao Paulo University who are adapting our work to their use cases, which is landslide modeling in the Sao Paulo region. And code and data are publicly available. So thanks a lot for listening.